what is the IP address, what is the name of the node, who has the content. With that info, it will ask, I'm looking for that in the file, and then also do a remote procedure call, which is read or write. Okay, so this is these slides are from distributed operating system. Remember in Facebook, the haystack, when we talk about it, there will be the photo upload, the write and reading, download, and also there will be delete operation, and it is done asynchronously. We use the word asynchronous, right? So asynchronous in an operating system, what it means is that this is asynchronous, this is asynchronous. So the client asks something, server responds right away. Doesn't mean that the work is done. It will be done later. It can be done later. So just it doesn't have to be everybody in sync. That's what it means. Asynchronous is good for quick response time, right? But there can be some inconsistency. This one cannot assume that the work is done at this point, right? Here's a client this way. On the other hand, synchronous remote procedure call will be that make a request to finish the work and then it replies to the client. Okay? So for a client's program, you have to wait for a while. This one, the waiting time will be a lot smaller. This one arrow is a little bit, in practice can be very short, right? So there's a concept for asynchronous one. The program progression can be fast, but the concurrency has to be made sure by the program manager. So just I'm introducing the terminologies for distributed file system. Think about in a distributed file system, here client and server try to access the storage over there. Something can go wrong, right? During the network transfer process. So in the program, you might say, I'm calling, calling for reading or writing of a file or data remotely. So remote procedure call, what typically you would assume that is that you call in a program, it will be done once and only, exactly once. Local procedure call exactly once, that's not difficult in a local operating system. However, when we have a network involved, then this can be, challenging. The things can go wrong in the middle, right? So even if you wanted to do once, writing once, for example, right? Or reading once, in fact, what can actually happen is that it may not be done because the server crashes, or whatever, the server itself or the process dies, or something, some things can go wrong. So it may not happen as the client's program wanted, or really, possibly done, or potentially it can be done more than once. Okay, maybe underneath clients, they thought that reply not coming, retransmission happened, and the potentially done more than once. So exactly once semantics, it's very difficult. You cannot assume that it's gonna, you can't. This is what we call the system level understanding. The people who are only at the high level, upper level, the programming or upper level development environment issue, they don't care, and when things happen, they don't understand. It's important for you to understand the system level issues. So, meaning below the user level application. In reality, these things can happen, right? can you do then? What can a distributed file system offer in terms of semantics? Again, exactly one semantics may be difficult to achieve with a remote procedure call over a network environment. So, what remote procedure call, meaning that the I/O operation over distributed file system, will offer in practice either at least one semantics or at most one semantics, not exactly once. So at least once means that at least once may be done, but that means more than once, right? At most once semantics means that either one or zero, okay? So that's what it means. That's what will happen in, that's what the distributed file system will offer in terms of remote procedure called semantics. So, if you are a developer, application developer over the distributed file system, you have to know what this RPC semantic is. Or, and then, write a program accordingly. If it's at most one semantics, you try to do it, but it may or may not be done, right? Then what can you do? At the application layer, you have to do, to the reliability checking, is it really done, right? So that's something that has to be done above the system level at the application. At least one semantics, you have to understand that this is what the semantics distributed file system offers. So if it's maybe you might have to check if it's done more than once, then you might find what is the earliest one, or what is the latest one, or whatever what you need to do for your application. So understanding the RPC semantics of your distributed file system is important for the application developers. If you were the distributed file system designer, if you are building the distributed file system, then you have to make the choice depending on the usage of your file system. So if you are at Google, for example, what would be the usage of these files, and based on that, you have to decide the RPC semantics for your distributed file system. Can you think of some application that at least one semantics is fine? Things can be done more than once. Operation, writing can be done more than once. Maybe something, I want to think about the example. Really depends on the application. We call it, so these applications, the applications that at least one semantics is okay would be like really binary. It's there or not, right? So it is yes, no, or on and off operation. Then on, it's okay, at least once, right? That's called that kind of operation is called idempotent function. Idempotent function, 1 times 1 is 1. 1 times 1 times 1, 1. Itself, the operation on itself becomes itself. That's it. So if question is.
It's like a live stream, like it's there. It's checking every time one is it live or not, like 0 and 1.
Right. Yeah. But you can also that can be street light. Is it on on a city monitoring? That could be something. what about just even all the multimedia, even Facebook types of,
Stream.
yeah, the multimedia, either photo, or it can be stream or static, right? In that case, at least once it would be okay. What do you think, Google? Do you think Google file data that's necessary for, say, Google search, online data, web data? Do you think at least once is fine?
Mm-hmm.
I guys be skipping.
So web data, you do Google search, and the Google server has to search the online content and give you answers. Do you think at least once semantics is okay?
No, I think it take.
At least once a week.
Okay. It is okay.
Okay.
Yeah, and I mean, think about why
You are searching for online content.
Okay.
Suppose the online website is changed, but that's fine. You want to be able to search up all the directories as many as possible. But some of the changes they might say whatever they are searching based on anyway in the older website. Could be day old or week old, right? So the maybe overwritten website, that doesn't matter. Can you think of some applications that does require, that is okay with the at most once semantics? What could be some applications where you don't want multi-writing to be done? You try to write once, but done multiple times. That cannot be tolerated. That's not difficult, I think. Bank transactions, right? You withdraw once, you really did it once, but somehow it was done multiple times, and your bank, is in minus. That's not what we want. And maybe adding it, you might be okay, but still, it's not a semantics you would expect. So really, depending on the application, distributed file system designer, depending on the most of the applications, based on that, the distributed file system designer has to decide on the semantics. Okay? So you might ask, what about that I'm a distributed file system designer? Most of application is okay with one of these semantics, but not everything. You can take care of it in the application. So Google File System was published in ACM SALSA, Symposium on Operating System Series, the 2003. Cannot imagine it has been more than 20 years. So this is one of the amazingly highly cited paper. So not just their solution, I really want you to look at how do they start from the motivation. Because the Google file system, as you already know, it has changed. Since then, Colossus or version 2, some of the design they thought it's good was actually changed a little bit, not a whole lot. But so it's rather than just the solution, it's really about how do they observe, analyze their environment, and then make a decision out of it. So at that time, Google had a lot of data. For example, web crawling, the whole online web, they crawl it. while you are not being aware of it, and they store it virtually, logically, in a big disk. And then that disk will be processed by servers whenever user makes a search query. So process from user's perspective, it's just a one disk and one big CPU. That's a logical thinking, right? But in reality, it does require a lot of CPUs. You already know, a lot of storage systems. Rather than having supercomputer, which is too expensive, they decided to go many small ones, right? So they decided to scale out rather than scaling up. They started with the Dell PCs, commodity chip PCs. PCs they used to have an industrial scale and more fault tolerant in terms of hardware that has been there. But their choice was that let's use just many chip ones. And then we put them all together for total aggregated the storage capacity to be big. And then let's use many CPU to the parallel processing. The question is how to share this data among multiple PCs, meaning that it does need distributed file system. At that time, available there were many, there are many available. Distributed file system is a really traditional build. And the NFS was the most popular one, easiest one. Ivy was introduced, and it was available then. So they can start with the NFS, like Facebook they had started, and then it will have a good unique semantics originally. However, it's difficult with the many one Linux system. This is good, but over network file system, when there's a server connected over a cluster within a LAN, it's difficult to have. So they changed semantics over NFS, and that is a close to open or session semantics. That's a compromise they made. Fault tolerance was not really good. Sharing, doing the thing that they need to do, basically it's okay. But doing well in terms of fault tolerance wasn't good. So I think I'm starting to chip PC. What does that mean? It can fail very often. Even expensive ones, still it can fail. If you have many. We talked about if you have a lot of children, there's something happens. If you have a lot of devices, there's just something happens. It does happen. Ivy it's more it was introduced available then. It has a better consistency. That does load store. But still fault tolerance was not good. So the thing it's in red color, meaning that fault tolerance is very important. And none of the things available then was good enough for high fault tolerance. See, you're out of the school and you try to do new things in the industry, in the real field, and the things you learned from school didn't help. So they do it from, they build their distributed file system. So Google File System is their own distributed file system that allows the sharing data on clusters with Google's application in mind, Google's workload in mind. Okay, so unlike traditional distributed file system environment, they had the different ones. Compared to that, distributed file system available then was not really Google scale. We were talking about 2003. still, it was a big scale. It's not for really large scale, not a global scale. Failure protection was not good enough. And network overload is an issue. There were multiple data centers, so they designed it. So, cluster environment within a data center, they will have hundreds, thousands of PCs, servers in a cluster, and there will be multiple clusters in a data center. Here I'm talking about hundreds and thousands, later thousands and tens of thousands, even bigger. What do you think UMKC data center number of servers? It will be magnitudes lower, right? Maximum 100, it could be lower. This is a question you want to ask when we have a guest lecture. The chip commodity parts in PC, meaning that they are fragile. They can fail often for many reasons. Software reasons, ad bug, OS bug, the human error, as well as hardware reasons, disk failure, memory failure, network failure, power supply, connector failure. Any components in whatever operation here, including human, can be a source of failure. So it does happen often. Before this, actually around this time, like I also in my program at that time, Sprint Research Lab in California, we have done failure-related analysis. In the industry, everybody knows things can fail, but for their public image, they didn't really disclose, those things. There was no little study done on failure analysis with the real data. And then at that time, including my group and people also acknowledge that failure does happen often. What we need to do is that we keep monitoring any failure and have a mechanism for fault tolerance and recovery. This is essential. Let's not hide it, but we have a scheme around it. So the first goal is to detect, tolerate, recover from failures automatically, not manually. You cannot do it manually in Google scale, right? And then they look at the file size, online data, web data, big. What's your average file size in your file system on your laptop? Maybe a few K to a few megabyte, maybe. Some movie, if you download it, it could be bigger. Typically small, your assignment file. It's not too big. But their files are really big. How big? More than 100 megabyte in size. And the application is mostly, they read it all and streaming reads, meaning that they read, at the end, done. They don't go back and read it again. Unlike your, maybe, the toy assignment programs that you have done, like a sorting algorithm, you read it again and this. It's not like that. Reading once. Writing, some differences, some small update, doesn't matter. We can just append it. New website appears. So the writing is really basically considered as once. Any updates considered as an append. So what they want is that they want the clients also, the multiple clients, the reading, they want the writing to be done also at the same time. They want that the writing can be done at the same time in parallel without too much overhead of the synchronization. Synchronization meaning that control is done to one server and other server cannot write. That's not what they want. And whatever writing, at least within the write, that they should have a meaning it should not be intervened. So basically not the update, append done by multiple clients. That's what they would want. You see, this is you might think that, well, okay, it's not too difficult to understand. It's not about difficult to understand, it's easy to understand. But how do they look at this? This is really entirely different from the workloads that they may have experienced from or learned from school. So in real life, challenges are always challenges, the unexpected. If it's expected, it's not even called challenges. Challenges happen all the time. And that's an opportunity for them to design a new file system, see how much impact they have to the rest of the world, entire world. All public clouds, not just the US, but anywhere. They have to basically listen. So this is from Google. Google influenced all public clouds, and also if you recall the later or even now later today, you can take a look at the data center tour video. Okay, they talk about they use the what kind of version of TCP they use. That one is from Microsoft Research. So those researchers in the field, the Microsoft Research people, they publish it, employed by Google. Google folks, they publish it, used by others as well. So it's not completely, it's open community, right? Not everything is open, but mostly. So here's the GFS architecture. Fault tolerancy is an important one, right? So
How can you provide fault tolerancy? With, if something fails, something else should be available. With redundancy, duplicates, right? And you want to have a duplicate at the file system level, right? Not above. If you make another, this file, assignment 6 is so important, I don't want to lose it, you make a copy, file name will be different. Another copy, file name will be different. That's not the reliability offered by the file system level. So here, file name would be the same. Underneath, there will be multiple replicas. Right? So then, always when we deal with a file, there is a metadata information, which is directory information. Right? Who are the servers? Who are the actual server? What are the files? What are the file attributes? And then which server, storage server, has the file? That information is a meta information, and that is done. That is handled by a server called here master server. In Hadoop file system, they call it name server. In Google file system, it's called master server. Okay? So the other one, if it's mastered, what's about the other one? It's not a slave server, okay? This is called, the other one is called chunk server. So this is a server too. Chunk servers are the servers too, storage server. But these, remember the directory server and storage server, and then client, the earlier picture. The directory server is basically, in this case, master server. And then chunk server is the one actually that has the file content. Okay, it will be many of them. So master server, how many? Logically, one. Chunk server, many. Okay, and chunk server has the file content, not like this server has this file. Servers are, files are big. You don't save entire file. You don't have to save the entire file in one server. You can actually spread file content over multiple servers, just like the RAID spreading. But here, the spreading is it's done across the rack as well. If it's all in the same rack, then the
fault tolerance will not be good. Correlation, one rack fails due to power issue, then all the data will be lost. So they spread across racks, but they also are mindful that the bandwidth between rack, intra-rack bandwidth is higher than inter-rack. Intra-rack, you will be that those are connected by a Tor, top of the switch, top of the rack switch, higher bandwidth, closer, higher bandwidth. Across the rack, you need it's more powerful switch, but usually it's shared by other racks as well. Therefore, effective bandwidth will be smaller. And then they have a chunk design. Chunk is a part of a file. It's a 64 megabyte, which is really big. Fixed size, that chunk here is fixed size. Fixed size, big size, part of a file, and there's an ID, 64-bit, which is really big. We are talking about the 32-bit 16-bit operating system, those things. 64-bit chunk ID is huge enough. That's globally unique. You don't have to do multi-level indexing to find out where it is. Maximum number of the chunks, maximum number of chunks, how can you find it out? With the 64-bit ID. So number of chunks, all chunks has to be unique, right? 2 to the 64, that many chunks you can find. Maximum data size, actually, theoretically, 64 byte times 2 to the 64, that will be maximum data size. These are the kind of operating system design questions. If you decide to use this many bits, what's the maximum data? And then many clients are actually basically this not you as a user, but you do a Google search. It will be taken by a Google server. That Google server is a client in this Google file system. Client meaning client for accessing data. Many of them can access it at the same time. That's design. So here's the architecture picture, the famous picture. GFS client is an application that needs to access the file. So it's not just one server, there are two types of servers. What are they? Master server and chunk servers. Master server, if you deal with the meta information, for example, file name, chunk index, I need to read this file from this file point, typically maybe from beginning or somewhere in the middle. Then this master server will give a chunk handle that includes the chunk handle so ID where it goes, and then chunk location, what's the IP address of the service for this file in index. With that, so question and answer, with that, hey, I need to read this data from this file chunk from there, and then just take one data message. Data actually will be transmitted to this application. Question? A little faster. So master server is the one who handles all meta information, including namespace, directory hierarchy, access control, mapping from files to chunk location of who are the chunk servers that has the chunks for this file, right? This is all the meta information. And then it also does other control information, which is a chunk list to servers. Chunk list meaning you chunk server, you data server. So chunk server in Hadoop file system name is name data node. new data node or new chunk server, you have a list of the chunk. Okay, so if some chunk server fails, master server will give a list to some other chunk server. And then some file may be deleted, then garbage collection. Some file may be deleted. You see that garbage collection, what does that mean? File is not deleted immediately, not synchronously, it's just marked, like Facebook. Most of the largest scale delete is not that important. Sometimes you want to keep it for user who might change their mind. So they just do a flag marking, and then occasionally they will do garbage collection, just like Java also does that. And this is a common strategy these days. And then chunk may needs to be migrated between different between chunk servers. Some chunk server died, it has to migrate into a different server. This is a big task to do. We set a one server, and it has to be done fast. It's done in RAM, main memory. Typically, file system index information, where is it? It's in this storage, right? That was the case for F4 as well. So that's why you have to load index table and then read it, and then there might be multi-level indexing. You have to read the disk many times, IO operation. It's done in memory. Does it ring a bell? Have you seen something similar? In Haystack, meta-information indexing was done in memory, right? So that's exactly, because storage, file system storage info, but they put it in memory. So meta processing is really fast. Chunk server, so master server and chunk server. Chunk servers are the one that has the data. What was the chunk size? 64. This number actually appears often, so it's not, this number may change, but it's actually good to remember. So they have it on a broker using standard Linux, meaning that this file system design is above the Linux. Okay, and each chunk has a version number and checksum. Version number to chunk may be updated, and for checksum is for error detection. Read write request will have the chunk handle and byte range. This chunk number 10, first 10 bytes. It's not going to be 10 bytes, but or could be entire 64 megabytes. That's the typically you have it in the read-write request. Think about your regular program, small code program. You will also say like how many bytes you're going to read next. And then here another thing is that chunks are replicated. See, fault tolerance was very, very important. Chunks are replicated in the chunk server level, and default replication factor is 3. Okay, so with the same file name, 3 replicas are there. And then one of the design decision they have made is that no caching of file data. Typically, caching is done. So if you open a file in your local Windows, the iOS operating system, you open a file, put it in a load main memory, and it's very likely to be read again. So another file open, it will be not going to the disk, it will be from your memory. So it is data file is cached. But in Google file system, they don't do file caching at the Google file system level. Well, what about the underneath Linux file system? That's okay. It doesn't matter. But they don't do Google file system level. you don't do extra file caching. Here, no caching is about the file data caching, and as you will see later, metadata caching is done. So a client, the application for accessing, file over GFS, what it does is that first of all, it asks master server about metadata information. Here's a file, what should I ask? Here's a range. Then the master server will give the chunk server handle and the location IP addresses, right? With that, client application requests the data chunk from chunk servers. Client does metadata caching, but again, no caching of the data. Metadata caching, you might read the file again, but maybe not the same part of it, because streaming read, that's the typical application, right? So if there is a caching, it's good for performance. However, the headache, issue could be consistency, and without not allowing caching, they don't have to care about consistency. Application typically streaming read, append write. It doesn't really, the benefit from having a cache. So this is their design decision. I hope all of these single line making the decisions, you might have a light bulb in your eye and, don't you say, wow, that's amazing. Okay, so any file system, they have to have an API, read, file open, read, write, closing, etc. So those API is it's really it's a little bit it's their own application. I mean, they have their own API designs, not exactly mimicking Unix or Unix implementation. So what they have, first of all, is open, delete, read, write. The least important one will be delete. You can imagine that it will be just cached, right? They also have snapshot and append. And this append is at least one semantics, as you can imagine. And this another thing that allowing gaps or inconsistencies among clients. These different clients might get a different answers. Think about Google search. You do the same application, you do a same keyword. The results, being a little different for different queries, that's okay. Maybe top pages usually doesn't change. Maybe that's out of maybe thousands of search results, a little difference with the same query, it's fine. So reading, let's see. We'll try to actually do it, and I might actually give you make it take the quiz afterwards, okay? So we have 10 minutes left. This is really exciting, but I hope you're really excited as I am. So the reading, here's an API, read, file name, and chunk index. So here's this is in client's application. Then response comes with chunk ID, chunk version number, location of replicas. Replicas meaning chunk servers. And so it's not master decides that out of 3 replicas, you choose the one. You choose this one. That's not what they do here. But who choose the
actual chunk server. So out of 3 replicas, it is client. Client choose that, oh, I see that there are 3 chunk servers that has this chunk. I'm gonna choose this one. Which one does it choose? The closest one. This is an important one. How do you know it's close? By the IP address in the rack. So here's the server. The here client is all the servers within data center too, right? So here I'm in this rack and maybe in the same rack or close by rack stored the server. That's the one I'm gonna read the data from, rather than another floor or anything like that. How does it know? By its IP address. Okay, so consider that 132.132.132.1 for and 132.132.132.2. You can imagine they are close, same subnet. Right? Even with the same subnet, the smaller one, you can imagine that that's the closest one. So that's how they choose. This closest one by IP address and client chooses. Can you feel this can be all the questions? Right? And then chunk server will reply with the data. That was for reading. What about writing? So key in the Google file system reading is that the closest one chosen by the client determined by IP. Writing, a client to write a file. You have to think about how you do that. Probably it interacts with the master server and get the IP address of the chunk servers where you want to do. But how many times do you have to write? It's over 3 replicas. So all the replicas has to be done. Of course, client doesn't have to say, here's writing, here's writing, here's writing. That's not a good option to do. But still, eventually, 3 replicas writing has to be complete, right? So for writing, there is another term or special type of server introduced. That's one of the chunk servers, but there will be one of them called primary for each chunk. The first part of this will be chunk is for this chunk, 3 replicas. Among those 3, this one is a primary chunk server for this data chunk. That lease, remember, master server does the lease of, does a lease, meaning the permission to save the chunk for each primary. But this primary is actually the one that is responsible to ensure that all 3 replicas are done with the writing. That's some important one, right? So it has to be reliable, meaning that closely monitored by a chunk server. Are you alive? Are you awake? Some students in the back. Are you awake? Right? The way, how can you, in a typical networking, the awake checking is the heartbeat message. Heartbeat, like, regular checking. Right? So typically 3 messages. Are you alive? Are you alive? Are you alive? You should respond yes, yes, yes each time. And if some node misses the heartbeat, say 3 times, consider that maybe that server is died. And have a kick in the reliability mechanism. So for writing, there is a special chunk server called the primary. Clients asked first of all, what are the chunk servers for replicas? And then all 3, here's another key term. If I ask you in the exam or next time, how does Jeff does reading and writing? For writing, you have to say this word. Primary, data chain, pipelining. These are the important words. If you write a long essay in the exam, if I don't see this word, you get 0. Okay. So 3
3 copy making, it is first of all the primary will take care of it, but to ensure that all those things are done. But it is done through pipelining in the form of daisy chain. Here's a picture. So a client, I want to write this file. Master say, these are the chunk servers, 3 chunk servers you have to write. Okay, and this is a primary, and these are not primary, secondary. Then what it does is that admin parallel. First of all, hey primary, I'm writing this one. Okay, and also at the same time, out of all 3, it just starts writing one of the earliest to closest one. Network bandwidth is important, right? So the big one is the data actually the transfer. I'm writing this chunk. And then client doesn't write from here to all of others one by one. Actually, the secondary replica, they know who are other replica servers. It will send it to the next, it could be primary or another one, and then another one. So this is called pipelining. You send it, well actually I didn't exactly explain it. So this is called, first of all, pipelining, that you don't send it from here, and then here, and then here, okay? It sends with a, client sends, just send it once, and then the other ones sends it, and then pipelining here, another meaning is that pipelining means that you start something before it finishes, it goes next, right? The architecture term, computer architecture term, right? So, don't you do a lot of pipelining in your work efficiency? If you think I do a lot of pipelining parallelism in my life. So here, the client just writes to the nearest, the closest one based on IP, and then these are all Ethernet in data center, right? It's a bi-directional. So while it is receiving, before the 64 megabyte is a big one. Before it is done, it sends it out. In and out happens at the same time. That's pipelining. And think about this. This is this. You see my hand motion? This. Not like this, right? Daisy chain. This is called computer architecture term, and computer science, the basic term, daisy chain. Okay, so let me stop here for today. I will extend your quiz time until midnight today, and this code is a Google file system, or we're all small. Oh, you don't see that? Some of the things I didn't get to explain entirely.
Still, read these slides and then do it. Okay.
Next Tuesday,
Going to library.
yeah, next Tuesday, I will have my TA to cover my class.
Right now.
We shall,
A lot of
or potentially we'll do. So I have it. I was thinking of having the AWS, the architect, giving a talk, as we have done many semesters before. The timing, it's I want to have him when I am with you. So this time I'm gonna use the last semester's his video. He has a tweet.
So that one, I might have it either on the last week or or some other time. Okay. So next Tuesday is not 100% decided. I want to make sure that Bishop is ready there. So potentially that could be next Tuesday. So look for the announcement. All right. Thank you.